Okay, this is the session, and Susana will make a lecture for 1 hour 20 minutes.
Okay. Yeah, so the first session, which is now, I'm mostly going to focus on control and basic theory of control with as little proofs as possible, but I will give some ideas. But basically, I'll set up everything that then I'm going to need for later. And then in my second session, which is after the break, I'm going to talk about the liquid films problems that I care about, which is very similar to the problems that Dimitrios was talking about yesterday. So hopefully I can go quickly through. This is all the models because they're almost all the same that we've already seen yesterday. And then actually talk about how to use all the things that I'll talk about now, which were mostly ODE based, to go and control PDEs that are relevant for this fluids problem. And then I bullied Oscar into coming and talking a bit about what he's been doing recently, which is on the same type of problem, but with a bit more realistic scenarios and harder problems to control. And then tomorrow morning, I'll talk a bit more about optimal control of PDEs and the different types of controls and different types of models. So hopefully that will make some sense. It will be interesting enough, and the 3 sessions will sort of be different enough that there's hopefully going to be something new in all of them. So today, or now, in this hour, what I'm going to do is talk a bit about why control, what do I mean when I say control, what do other people mean when they say control, because sometimes it's different, and then talk you through all the concepts of control that I needed to learn to do what I'm doing. There are definitely not all of them, and there's a lot of places where you can read more rigorously about what all this means. And then what conditions we need to verify to have controllability. And then once we know that we can control something, how do we actually go and control them? And I wrote there some examples. There's only going to be one. So this first hour is going to be mostly like text and definitions and something, so it might be a bit boring. But then the other 2 talks have a lot of nice results and figures and videos. Okay, so why do we want to control things? We want to control things because we like to know how we like to make things happen. We like things to work in the ways that we want them to work. And so a lot of things that now are very trendy to control are things like self-driving cars or drones or having like robots. This is a photo of a video on a talk that I once took a screenshot of, which had like this robot moving around and avoiding people. There's a lot of people around here that will then walk in this thing, and the control has some feedback mechanism, which we'll know what that means in an hour, that makes it avoid people, or makes it actually, the goal is to have that robot moving in such a way that it optimizes how people move. And then you can do all sorts of other things, like try to control how crowds are moving by putting different lights or lighting mechanisms in rooms or corridors. And you can have all sorts of other things like drug delivery systems. Or in our case, because we're in an interfacial flow summer school, we're going to want to control interfaces of fluids, and that's what the second talk is going to be about, which is why I didn't include it here. But yeah, so there's a lot of types of control, and when people say control, they can mean a lot of different things. A lot of the time when you read a paper that says control of something, it will be like, I added this term to this equation or this right-hand side, I made it this, and then I made it that, and then I made it that, and thing number 2 made the system do what I wanted it to do, so I controlled it. So that's like the most basic thing you can do, is trial and error. Which is what I just said. You can do what sometimes people call passive control, but actually an optimal control, which is one of the things that I'll talk about a bit later today and most of tomorrow, which is you have your model, you introduce some control mechanism on your model, and then you optimize that. And then you apply that to your physical system and see if it works. What you can do that it's a bit better is something called feedback control, which is most of what I do, which is I have my model, I have my control, I apply that control, I see what my system is doing, and then informed by that, I update my control, and I keep doing that. That's what this figure sort of does, this is one of the figures that you'll always see in a control talk. You have some input which is your control or something. There may or may not be some error. You put it into your system. This for us is like our Navier-Stokes equations or PD solver or something. It outputs something, you observe it, and then you bring it back to try and do and make the system behave like you want it to. Okay, so yeah, so as I said, I will focus on this last type of thing for all of today, and then some of tomorrow I'll do some of the other things. Yeah, this is the type of control that I'll use, but I'll introduce that a bit better in an hour or so. Okay, so this is what people mean for control, and so and then from this, then people start building theory on what it's like to control things. So to start with, I'll start with an ODE example, and hopefully that will motivate what we're doing. So say you have an ODE. I guess this is the simplest type of ODE you can think of. The derivative of x equals to lambda x with some initial condition. What's the solution of that? So, questions don't work, as we saw. So the solution of that is the exponential function. So your function x of t is your initial condition times exponential lambda t. And once you know this, you know that when time goes to infinity, this will go to 0 if your lambda is negative. It will go to infinity if your lambda is positive. It will oscillate if it's complex, but I'm not gonna worry too much about complex numbers. But every time I say the word eigenvalue is negative, usually I mean has negative real part. But I'll most of the time say negative real part. Yeah. So this all works for complex eigenvalues. So this is nice, this is easy, this is sort of obvious. And I think the first thing you sort of want to do is, okay, what if I wanted, what if it goes to infinity? What if I actually wanted my thing not to go? What if I wanted to be bounded? What if I wanted it to go to 0? Then what you can do is say, okay, let me add some term to my equation, to some right-hand side, function u of t. What does that u need to be so that I get the desired outcome? And that's, again, not very hard to see that if I choose my u to just be a multiple of x here, then your ODE becomes that ODE with angle replaced by lambda minus alpha, and then all you need is that lambda minus alpha is negative. Right, so in this case, even if you had something that went to infinity or behaved badly, you can cook out a right-hand side to put there that will make things nice. It will make things go to 0, which for us is nice. Okay, so yeah, and just some terminology, we say that we stabilized the ODE. So we added some term that made the 0 solution stable. Anywhere you start, you end up with a solution that goes to 0. But again, this is easy. Real life usually is a bit more than one ODE. So say that instead of an ODE, we have a system of ODEs where now A here is a matrix and X is a vector. And you still have that control U over there, that again is a vector. For now it's going to be the same size of X, but it doesn't have to be. And then you have a similar thing here. So again, this F should be a U, sorry about that. So if you don't have a control over there, the equivalent to saying my solution went to 0 if lambda was negative in this case is my solution goes to 0 if all the eigenvalues of A are negative or have negative real part. Right, so the solution is still like it's a matrix exponential where you know how they behave. And so again, if you just have that U over there, you can do almost the same thing. You say your control U is some function, some constant alpha times X, which, because we're working in matrices, is convenient to put the identity matrix over there. This is the same control as before, and you still stabilize the system. Right? So now you can find alpha by saying you need the matrix A minus alpha I to have negative eigenvalues. So it's exactly the same way as you did it before. Okay, but the point is, the point of control theory is that you can do better than this. And most of the times, also, you can't make your U actuate everywhere. So, for example, if you have if your system has like 3 equations for, I don't know, position, speed, and acceleration of a car, you might only be able, usually you're only able to actuate on like your acceleration or something, or on your speed. Like you hit the brake or you hit the accelerator, and that makes everything else change. But you're not actively controlling everything, you're controlling one of them that influences the others. And so you do that by adding another matrix here, so this matrix B, that gives you that information. So this matrix B then makes your control be able to do a bit less things to your system. But it encodes what you're doing there. And again, later on when we start talking about fluids, I'll give you examples of what this can be. And so this is sort of the full control system. You have your linear system behavior, and then you have your control behavior. And in a similar way, you sort of still, or your first guess can still be, my control should still be proportional to my solution. It's just that proportional doesn't look like this anymore, because the sizes of the matrices don't have to be the same. Yes, but if you choose the control to be proportional to x, you just still say u is some matrix times x, and then you multiply that matrix times b, and you still have then at the end a linear system for x that you're saying, okay, so if the eigenvalues of then this big matrix are negative, then I can still drive my system to the solution x equals 0. And in fact, you'll be able to drive it to almost everything depending on some conditions. So usually when people are talking about control theory or linear control theory, this is what they mean. They're looking at a problem that looks like this. And then the whole problem is, how do we find this matrix K? So that's mostly what we're going to be talking about today. The last step of control theory, and I won't talk much about this now, but then Oscar will talk about this a little bit when we talk about the full fluids problem, is, okay, in the real world, it's not that you just, you might not be able to actuate on everything or control everything, but also you might not be able to control everything, to observe everything. So like, for example, if we want to control the temperature in this room, you might have a thermostat somewhere around here and a thermostat somewhere around there. It tells you what the temperature is right there. It doesn't tell you what the temperature is over there. So these systems have a finite number of observations of something, and then from that they try and work out what's the temperature everywhere, so that then they do whatever heating or cooling that they need to do to give you the desired temperature. And so you add an equation to your system that encodes this. So you still have the same problem. You want to solve my x evolves with some linear function that has some linear evolution and has some control there, du. But then instead of being able to observe x everywhere, I observe y instead, which is some operator micro x. So before, the system from before is exactly the same, where that matrix C is just the identity. But then if I can only see half of the system, or if I can only see the system at a few time steps, then I can encode that like this. So this is the full problem. And then in this case, you would want your controls to be proportional to your observations, which then will still be proportional to x. But then you're trying to find that matrix K such that this even bigger matrix A plus B K C has eigenvalues with negative real part. And this is much harder to do than the previous case.
Is that y equals cx or u equals cx?
Y equals cx, and then u equals k times y. So you have some observations, and then your control is going to be a function of those observations. It still all works out as being linear, because everything is linear in this problem. It doesn't have to be, and there's a lot of theory for it being for the nonlinear case. Okay, so yeah, again, as I said, the main question of this whole thing is to design controls, and that means how do I find this matrix K? So I assume I know what A and B and C are, and then I want to find K. There is some theory that I'm not talking about that, but it's possible to add noise to everything, both in the observations, because you don't have perfect observations of the system, and both in the the linear evolution as well, but that then gets too complicated too fast. So I'll just focus on this. And before I tell you how to solve the problem, I'll talk a bit about some definitions, and then I'll talk a bit about as well what happens when we have nonlinear systems, because at the end of the day we will be solving the nonlinear systems, so we need to still have that in mind because everything here is linear. Okay, so again, just to remind you what the problem we're trying to solve is, we say that a control transfers an initial state x naught to a final state b at time t if you start at x naught and you end at b. It's just a definition of transferable. And then once you have that, you can define that, or you can say that a system is controllable if you can find a control, or if you can find a matrix K such that you can reach B from x0 at some time t. And so it doesn't really matter how long it takes, as long as you can go from anywhere to anywhere else, then the system is controllable. And it's stabilizable if you can find, well, if you can find a matrix K such that the matrix A plus BK is stable, meaning it has eigenvalues with negative real part. And stabilizable is sort of a subset of controllable. In the end, everything's going to be equivalent. But so what you can prove is that if you are able to drive the system from anywhere to 0, then you can drive the system from anywhere to anywhere else. That's why people sometimes talk about controllable or stabilizable in the same sentence. Okay, so how do we go about actually controlling and seeing how things work? So there's this very convenient theorem called the Kalman-Rank condition. So again, this is the system we're solving, and I mean there are versions of this that are weaker, there are versions of this that are stronger, there are versions of this that include the observations, but they're very similar, so I'll just go with the system assuming that I can observe everything, so C is identity. So you take your system, you define this big matrix that depends on your linear evolution A and your control actuation B, and so that matrix is B, then AB, then A squared B, etc., until AN minus 1, n is the dimension of the system. So this is a big matrix that has n rows and n times n columns, where n is the number of controls that you can do. And then what you can say, and the much more detailed version of these theorems and a lot of other conditions that are not really relevant for us are in this book, which is very nice. So what this says is you can go from 0 to anywhere at some time. And this is equivalent to being able to control the system, and that's equivalent to being able to stabilize the system. That's what I said earlier. So if you can drive anything to 0, you can then drive anything to anything else. But then the really useful thing for us is this fourth condition that's called the Kalman-Rank condition, which is you can do all of this if and only if the rank of this matrix is n. So if this matrix has full rank, then everything is nice and you can do pretty much anything you want. If that matrix doesn't, then everything breaks. And I'm going to go through a bit of an idea of how this works, because I think it's nice, but I'm not going to go for more proof or anything. There's this really nice set of lecture notes by Evans, the same PDs Evans. He has lecture notes on everything that I like, of course. So I'll just focus on the rank condition because the others are really driving something to 0 and then driving something from 0 to everywhere else. And the idea is you write your solution of the ODE. I mean, again, this shouldn't be a surprise. So you have your initial exponential part, and then you have your right-hand side. So your control acts like this. And then what you do is, okay, if the system is stabilizable, then there exists some time t that you get to 0. Okay, and so for every initial condition x0, there exists a control u and a time t, such that your x0 equals to this integral, right? Because then if this is 0, you just send this to the left-hand side, e to the 8 is cancelled, so you get your initial condition equal to this integral over here. Which is okay. And then what you do is you assume that your system is stabilizable, but the rank of the matrix is not n, and so the span of the columns of that matrix, as I mentioned, smaller than n minus 1. And what that means is that there exists a vector somewhere in Rn that's orthogonal to all the columns of that matrix. And then you take that vector, you take the inner product, or you multiply that by every column of the matrix. And what that gives you in particular is that bt times all these entries of that matrix, so b, ab, an minus 1b, etc., it's 0, because it's orthogonal to every column, so in particular is orthogonal to each of these things. And so what you do then is you use Cayley-Hamilton theorem, which if you don't know what it says that if you have a matrix and you take its characteristic polynomial, which is just a polynomial that then gives you the eigenvalues, then if you apply that polynomial to your matrix, then it's 0. And so you use this thing together with induction to show that from here you get that this term here, b transpose a k b, is 0 for all k, for any power of a. And then you do a lot of matrix exponentials and rearrangements, and you work out that because bt a to the power of k is 0, then this matrix exponential here sort of has to be 0, and so bt has to be orthogonal to your initial condition x0, for any initial condition x0 that you can cook up. So bt has to be orthogonal to every vector in Rn, and so it has to be 0, so it doesn't exist. So this is a contradiction to the rank not being n. And then the proof on the other side is very similar, so you assume that the problem is controllable, and then you show that the rank has to be n, and you have to define some sets like this. Like the idea of the proof is sort of the same, but it has a lot of technicalities and definitions, so I won't go through it in very much detail. But the idea is you define the set of all the initial conditions that can be sent to 0 at some time, and then you define the set for all times. You can show that it's convex, and you can show that the system is controllable if 0 is inside of this set. So if you can send 0 outside of 0 and back to 0 is sort of what this is saying. Okay, and so controllability then means that you can send x0 to any other state canonical A. And so if you assume the system is not controllable, you can assume that the 0 is not inside of this set. And then you use some arguments that have to do with convexity of this to find then a vector b that's going to play the same role as before. That b will have the same thing, and then you show that the rank cannot be n. So the proof is sort of the same, but it uses a bit more technicalities about convexity. And yeah, so that's the main idea. All the other proofs are really about like matrix exponentials and a lot of algebra, so I didn't want to put them in a slide, but they're all in the book by Samson that I showed earlier. And then, as I said, there's like you can define, like I just defined controllability. Usually you have to define observability and detectability, which is like, can I learn all my system by a few observations of its behavior? There are very similar results to this that you can apply to that, and then you put them all together to solve that big system that includes observations and control. I'm not going to go through that in a lot of detail. Okay, so as I said earlier, and all that I said so far is for linear systems, and I guess almost all of us here will be caring about nonlinear systems. And not just nonlinear ODEs, but also nonlinear PDEs, and I'll talk about PDEs later. So if you have a system that's nonlinear, so you now have your evolution of x that depends on some nonlinear operator of x and controls u, then you have, you can still do the same thing, and usually what you do, and I'll show you how to do this to a PDE later, is you linearize around the zero solution, or whatever solution you want to stabilize. It doesn't have to be the zero solution, I'll draw this later. And then you stabilize the linear system. The first thing you try is to stabilize the linear system, because especially if you do it early enough and nonlinearities haven't developed, sometimes this is just enough. And then once you stabilize the linear system, you take your small perturbations, or any perturbations, and you then see whether the control that you have also deals with nonlinearities. So usually what you do is you find the Lyapunov function for the full nonlinear system, and if you find the Lyapunov function, you can show that it's stable. And again, I'll show you this working later for a PDE, because I think that's nicer than showing all the technical results. And again, so this is more or less simple to do for ODEs and for systems of ODEs, and as I said, we're going to look at PDEs a bit later. In particular, I'm going to show you how this all works for the Prometheus-Wyszynski equation, which is one of the equations that Dimitrios derived yesterday. Okay, so that was all about these things exist, I can do them, and a lot of the time, especially if you're reading papers about controlling PDEs, a lot of the time they're going to be like, okay, I proved that an optimal control exists, I'm going to move on in my life. And then they don't go and actually compute it, which frustrates me a lot. But yeah, so once you know that your system, that you, in theory, are able to control your system, what then you want to do is how you find that matrix K that will give me all my negative eigenvalues and all my stable things. So there's probably more than, well, there's a lot of ways you can do this, but if you're looking at ODEs, there's usually two ways that you can go about doing it. So the first way is called pole placement. It is called pole placement because you are assigning eigenvalues to your system. So you're saying, okay, my system is unstable. If it is unstable, at least one of its eigenvalues are negative, are positive. I want to find that matrix K that gives me not only that all those eigenvalues are negative, but also, I don't know, for some reason I want one of them to be -5. So this can be good, and I'll show you an example of when this is useful later. Because if you really want to make sure that your function decays at some rate, then this is good, because you can make sure that your eigenvalues are all smaller than that rate. And so if everything is linear, it should work at long times. Then what can happen is that you can have unexpected transient behavior. So you can guarantee that at long times it will go to 0, but you don't have any guarantees on what's going to happen between, I don't know, time equals 0 and time equals 5. The alternative to this is called linear quadratic regulator, which is an optimal control problem, and gives you control on the transient behavior, because you can tell the system, I want my solution to be as close to 0 as possible for all times. But it can behave poorly if you have 0 eigenvalues, and I'll show you an example in a second. Before I show you an example, I'll just say how this algorithm works is a bit complicated. There's a lot of linear algebra there, but there's also like a lot of really nice results about this algorithm that say, even if you get things a bit wrong, this is robust. So even if I make an error, everything will still work, and it shows how the algorithm is constructed in this paper here by Kotsky et al. But the linear quadratic regulator, I'll discuss it a bit, because then it's relevant for what's coming next. But before I discuss it, I'll show you an example here of what I was saying about what can go wrong. So this was just me yesterday trying to come up with an example to show this working. So say you have some 3x3 system where your ODE, I should have written the ODE, but anyway, so you're solving x dot equals ax plus bu, where A is this 3x3 matrix, I just divided it by 25, so that when I plot this, it ends at 1500 rather than that times 25. And then I'm assuming that I have one control that can act on the second and the third entities. And I just randomly generate an initial condition. So this matrix, I did not write the eigenvalues of this matrix, but one of them is 0, really, and the other two were small. So if you then simulate the uncontrolled behavior, then all of the components grow exponentially, because one of the eigenvalues is positive, and they influence each other because so they all grow exponentially. And then what I did was I computed this matrix K. On the middle one, I computed it using the pole placement, so I told the thing that I wanted the eigenvalues to be -5, -2, and -1. This would have still worked for smaller eigenvalues. I didn't have to change them like this. I changed the 3 of them, just because I wanted it to go to 0 fast. But if I wanted to change the system as little as possible, I would leave the 2 negative eigenvalues to still be negative, and then just change the other one to be small. And you can see that all the 3 components end up at 0, but before they end up at 0, they do crazy things. And so this one comes to -5, this one comes to -200, before going back up. And this happens a lot in this problem. So this is something to be aware of. But on the other hand, this might still be preferable, because when you're doing the application later, if you start with an eigenvalue that's 0, which we did here, that's why we put this matrix like this, then you're not always able to make all the 3 eigenvalues negative. Like the algorithm sometimes really struggles unless you look it up well to make the 3 eigenvalues negative. So we made one of them -1.4, which was way smaller than the original eigenvalues, and the other 2 are very, very close to 0. So this will probably eventually reach 0. They're starting to decay, but it will take much, much longer. But it will never go away from the initial condition, which made them 1. So this stays between -1.5 and 1, this stays between -2 and 1, this stays between -2 and 2. So with LQR, you have much more control of what your solution is doing as a function of time, but you might not always be able to reach the 0 if you have a 0 eigenvalue. Whereas with this one, if you only care about what your solution is doing at 1 times, use this one. But then you don't have control of what the solution is doing. And this can cause problems if you're actually trying to prove things in the sense of if you're working on a nonlinear case, you sometimes need bounds on the solutions of your problem, and I'll get back to this when we're talking about Holroyd's Cauchy equation, and if I'm not asked, because I might forget, this can be wrong. Yes.
If you do a calculation every for a long time, is there a possibility to use?
Yeah, it probably will, because this still has a negative real part. It's just that this is so close to 0. That will take exponentially longer. I think I ran it up to 5,000 and it still hadn't reached. So this one looked very boring and you couldn't see. So I wanted a time interval where you could see this really crazy thing and this not then. But yeah, so if you leave it for 1,000 times longer than this, then you'll eventually get a really very long time. And sometimes you can do that, but sometimes you can't wait that long for your system to do its thing. Okay. All right, so let me talk now a bit about how you actually get that matrix K. How you actually get that matrix K is you open MATLAB or Python or something, and you click place, and that gives you the K with pole placement, or you click LQR, and that gives you the K that gives you the best cost. But it's actually nice to know how these algorithms work, because then you can tweak them or you can make things better. Okay, and again, for simplicity, I'll consider that I have full observations, but this all sort of works with non-full observations. So what the LQR control does is it's minimizing a cost function that I'll explain in a second, subject to your X solves your ODEs. Okay, so what you do here is, okay, if I want to stabilize, I'm running my algorithm from 0 to infinity. That's why the LQR was taking a very long time to converge, because that problem, the solution to that problem actually guarantees that at time it was infinity, it will be 0. You can change it to make up then it becomes harder. And then what you have here is just X transpose Rx plus E transpose QU, whereas R and Q are symmetric positive definite matrices. If both of them are the identity, then this is just the norm of X and the norm of control. So you want to minimize the norm of your solution, so you want it to be as close to 0 as possible, and you want your control to be as little as possible. And then what you can do to tweak, and I could have done that to the previous algorithm. In the previous algorithm, I just used R and Q to be the identity matrices. So I said, I give the same weight to my solution and my control, just give me the minimum, but I can say, actually, I don't care how strong my control is, I care that this is close to 0, so I can make this Q a variable 0.1 times the identity, or this 10 times the identity. Or I can make it any symmetric positive definite matrix. So if you know things about the system, then you can actually choose these matrices in a smart way that then make sure that this is happening. So that's why it's important to know what your system is doing. But yeah, basically that's what's happening here. I'm minimizing how far I am from 0 and how much energy I'm putting in my controls. And I can then actually, I can make this any other state. It doesn't have to be 0. I could have an X minus B here and X minus B there if I wanted my system to go to 5 or something. And so once you have that, yeah, so this is just to say if I want it to stop at a finite time, I then have to add like a final condition here, but it still works. The theory is more or less the same. The problem is just much harder to solve. Okay. But so if you are like, there's a lot of ways you can solve this, and you can just if you have a finite time, you can solve it just using Lagrange multipliers. So I don't know, are people familiar with Lagrange multipliers? Some yeses, some confused places. So the idea is you want to minimize this subject to that, and so you make this, instead of being constrained, you make it something that you want to apply to minimize as well. So your cost function is the same, and then you're saying, okay, I'm introducing a new function, lambda here, that I'm then multiplying by my state equation. So if my x and u solve the ODE, then this can be anything because this is 0, but if this is not 0, then you get some information on the problem. And so typically what you do in optimization when you have a problem like this is, yeah, you introduce this new variable lambda, you put this together in a cost function, and then you minimize this new bigger thing that has more variables. Gives you more space to move, and usually then what you do is, if you take variations or derivatives of this with respect to lambda, you get back your state equation. So if you take the derivative with respect to lambda here, you get this, so you get the state equation. But then if you take the derivative with respect to x, you get a new equation for lambda. It's called the adjoint equation. And if you take the derivative with respect to u, it will give you a kind of optimal control. So let me show you how this looks like. So you take your Lagrangian function, you take the derivative with respect to u is here and here, so you get that your QU equals BQ alpha. So you sort of take this B to this inner product on this side, you take a transpose. So this gives you that your candidate optimal control is a function of this lambda function that you just introduced. And then you take the derivative with respect to x. To do that, you sort of integrate by parts to pass this derivative to the Lagrange multiplier, and that gives you an ODE for the Lagrange multiplier. So which is the same as before, but where your A is transposed and your X appears here on the right hand side. But because of your integration by parts, you take a minus sign in your vertex. So this equation runs backwards in time. And so you need a final condition. So what you can do here is actually, and that's what people do a lot in optimal control, or dependent, especially if you have a nonlinear problem. This is all linear, so you don't have to do it. But you can do that. But you can start with some control Q, say, I just have a guess. You solve your equation for X forwards. That gives you the final condition here, X T. And then you solve this equation backwards. And then you plug this back into your control here. And then you do this again, and again, and again until it converges. So that's, in theory, something you can do. But because this is all linear, you can do something a bit better. I'm not going to go into much detail about this, but you can, very fast. In this case, what you can do is you obtain this matrix impact equation, which then you solve. If you're able to solve this, then your control is the solution of this. I'll just tell you how it looks like in this case, because that's a bit easier. So again, this is pages and pages of a book that I didn't want to put in slides, but the idea is, okay, if I assume that my u is some function, if I assume that my control u is proportional to x, then this whole thing here, without the Lagrangian part, can be rewritten as a function of x, right? So it can be x transpose times r plus k transpose q k x, right? So if I have x dx, x drx plus u t k u, and then u is kx, you get this. So you can break this together with that, and you get this expression. Okay, and then what you do is you say that you can write this as a derivative of something, so you call this something, you call it the derivative of something, you work out what this derivative is, and you end up with this equation here. Okay, and so this is something you solve. Again, you go with MATLAB and write care or there or one of those. It gives you the matrix P, and then once you know what the matrix P is, you plug that into here, and you get the same thing. But again, and then this is sort of like a intuitive way of thinking about this problem, but then once you have this, you actually have to go and prove that, first of all, this is a thing that controls your system, and second of all, that actually it minimizes this initial function. And that's sufficient. As long as everything, all those controllability conditions work. Okay. And yeah, so Oscar, when he talks about this part later, he will actually tell you how to, an idea of how to do this when you have observations, but also talk a bit about how to solve this numerically, because this is not obvious. So these matrix systems, they're sort of easy to solve for small dimensions. So if your matrices are small, but the moment you start having very large systems, which often you do when you're looking at PDEs, then this can be a problem. And there's like people who, their research is all about how to solve that efficiently. It's not something that's very obvious how to do yet. Okay. Before I finish this part, and again, I went way quicker than I expected, sorry about that. What do we do when we have PDEs? So PDEs are infinite dimensional systems. So you can think of a PDE, and that's what most of the next 2 lectures are going to be about. You think of a PDE as an infinite system of ODEs. think of it as if you Fourier transform, you get an infinite amount of Fourier coefficients and you can treat your 2D with that. So the space where solutions live are not Rn anymore, but they're usually a manifold or a Hilbert space. And so your matrix A is not a matrix anymore, it's an operator, it can be a differential operator or anything like that. And the other matrices are also operators. And so in practice, what you would need to do, and what some people do, and this is a really good example of that, is the main person I know that's working on control of PDEs in the ways that we do, is you look at, again, you look at your PDE as an infinite system of ODEs, you think of semigroups and a lot of algebra that I don't know, and then you prove things for it. But the whole point is you have to think about this as an infinite matrix with an infinite number of eigenvalues. How can you prove that all of them are negative? Okay, and again, passing this is not straightforward. Even for linear PD, even for the heat equation, there's still people doing control of the heat equation. Because if your boundary conditions are funky, then you might have problems. So it's not like this is something that's known and that's done. Yeah, so later today, actually probably still within this session, I'll show you a bit on how we do this for the Coulomb-Sufficiency equation, which again is one of the equations that Demetrius showed earlier. So, okay, I was hoping to go through this in an hour. It took me 50 minutes. So is it okay if we take like a 5-10 minute break now and then I do 20 minutes before the other break? Cool, thank you. And we'll come back in whenever Jack tells me I should, or Sasha tells me I should come back. Thanks. Oh, Jack, wait.
Ah, yes.
Or do you want to do the...
Yeah, make sure in this break.
Okay.
Are you going to stop?
Pause capture.
Just waiting.
Oh, it has the wrong thing there though.
2 minutes. It could take time.
Yeah.
Yeah.
Done.
Yeah.
Okay. Okay. Welcome back. So I'll continue until the actual break so that we can go have coffee, but actually I think I worked out a good way of doing this. So as I said, like the last hour was everything very quickly that I sort of needed to know about control theory to be able to do what I'll do now. And now I'll actually talk about the interfacial flows problem that we work on. And so until the actual break, I'm going to talk a bit about the problem that I'm concerned about. I'm going to talk about the models that I use, or that people use to model them. And again, Demetrios already went through how to get to them yesterday, so I'll just go over a quick reminder of what they are. And then I'll sort of set up a bit what I'm going to do for the rest of the thing, and for the rest of the hour, I'll talk about how to control the Coulomb-Sufficiency equation that I already said like 5 times today. And then what we do for long-wave models, which are a bit closer to reality, and how we're then working with Radu about applying the controls to DNS and actually seeing if this is going to work in the real world or not. And then he'll actually tell you how to make these things happen. And I'm told that you might actually make it happen yourselves in some examples. So that's, yeah, exactly. Okay, so here are falling liquid films. Here's me, very happy next to one falling liquid film in Bristol, I think. So again, this is the figures that most people will show you when they're talking about falling liquid films. So they're like very thin layers of liquid going onto some flat, in my case, flat substrate, like when it's raining, or when you're having a glass of wine, or when you're happily being a tourist somewhere. But this, again, I think is a classical problem. Most of you will have heard about it, and if you haven't, you had yesterday. But they are useful for a lot of things, like, for example, if you are manufacturing screens, you want to coat these screens, and you want that coating to be as smooth as possible. Or if you're trying to cool something like microchips, you want this microchip to be like corrugated so that they have a lot of surface area so that you increase heat transfer. So my motivation to work on this is, okay, these films have an interface, and I want to make the shape of that interface whatever I want, really, for the application that I care about. So this is how they look in an experiment. So you have a film, this one I think is vertical, but you usually have an inclined plane. Depending on the inclination and flow rates and things, your system might be stable, so you'll have a flat solution, or you can start having traveling waves that travel downstream, or in some extreme cases, you actually start having 3D wave behavior and chaotic solutions. So this is like very rich, and ideally you want to stop something like this from happening, and then drive the system towards either having a flat interface or having an interface with a shape that you can control, and you can control its speed and what it's doing. So what I now want to do is, okay, how do I use the theory that I just talked about in the last hour to control something like this? So the idea of what we're doing is, okay, so you have your physical system, you have your film in an inclined plane. Here it's horizontal just because it's better. You have your full model, which is Navier-Stokes equations. I'll write them down in a second. You have some what we call virtual experiments, which are DNS simulations of the problem, which again, you'll hear more about this tomorrow. And then what we do is we have these reduced order models that Dimitrios was deriving yesterday, and we do control on those models. And then once we have control of those models, how can we use these controls that we learn in the actual DNS? Will they work? If they don't, what can we do to make them work? So that's what the rest of today and a bit of tomorrow is going to be about. So here's the film. So you have, we'll do everything in 2D, so our equations are going to be one-dimensional. And I'm also going to work on periodic boundary conditions. So whatever leaves this way comes back that way. This is a reasonable assumption as long as the domain is long enough. If it isn't, then you have to impose boundary conditions, and it's not always clear what they should be at the exit or at the entrance. So I'm not going to worry about that here. And then I have my interface at y equals page of x p, and my time is at y equals 0. And I'm going to assume that at some locations in my domain, I have some holes or something where I can pump fluid in or out of the system. And then I want to decide how much fluid do I input or take out of the system so that my interface goes to some design shape. So, as I said, the full model for this is Navier-Stokes equations. I already wrote them here non-dimensionalized. We have a Reynolds number, and we have the inclination angle theta, and there's a Euclidean number that's hidden in a boundary condition that I didn't write, but the boundary conditions that we face are the same that Dimitrios showed you yesterday. The main thing that changes is that now at the wall, the bottom wall, I no longer have v equals 0, I have v equals magnitude. I have a function f of x in time, and I want to prescribe and find out how to prescribe it so that I drive the system to what I want. And I think we all know that we can't do anything analytically with this problem, and it's also very computationally expensive, so you don't want to do optimization and control here. You want to develop things in models so that then you can apply them directly to your problem, and hopefully things will work. So it's important to get models that are accurate, and when you control them, you know you're controlling the right thing. So which models are we looking at? So we, first of all, in the same way that Dimitrios did yesterday, so we take advantage of the fact that the films are thin compared to how long they are. So I'm assuming that the length of this is capital L, this is big, and height is h0, which is small. That gives you a small parameter. You can do asymptotic expansions to get an equation that looks like the Bayesian equation, which is, I'll write it down in a few slides. But this is the one that Dimitrios showed yesterday with the h cubed and the third derivative and the second derivative. That gave you a fourth derivative and the second derivative, etc. And as Dimitri said, in the lower cases, this blows up in finite time. This is not well posed, where it's good in some parameter values. And we also consider a weighted residuals model, which I don't think you did yesterday. I'll talk a bit about it later. But you do a similar thing, so you still expand your solution in powers of epsilon, but then what you actually you expand it as an logarithmic expansion on an appropriate basis, which then will have the powers of epsilon in it. And you make those basis functions match the boundary conditions, and then you get, instead of getting a PDE for the height like we did yesterday, you get two PDEs, one for the height and one for the flux. And again, I'll show you what these PDEs look like maybe in an hour or so. Okay, so these models are good for the approximation of this. They agree with Navier-Stokes equations regarding critical parameters for stability, but then they have all the problems that Dimitri was talking about yesterday. So they're still nonlinear, so they have complex dynamics. You still can't do anything or almost nothing analytically here. And if you want to solve them numerically, especially with controls with the shape that I have, which are very localized, your matrices are not necessarily very sparse, since the numerics get a bit stiff. So you need to be careful and solve them. And again, for this reason, we do exactly the same thing that we did yesterday, which is to assume that the derivations are really small, do it with nonlinear analysis, and then you end up with the Gomes-Mashinsky equation for a perturbation of the interface. So in these two models, a flat interface for me would be an interface at h equals 1, and then I say that I have a small perturbation to h equals 1, and the controls also need to be small compared to that, but that's okay. And you end up with a controlled Gomes-Mashinsky equation. So this is very similar, but with some different coefficients that the Dimitrius had yesterday, just because there is a different change of variables. But I'm solving this fourth order PDE with a Warwick type nonlinearity in a periodic interval 0 to pi, and the important thing here is this coefficient mu, which is usually smaller than 1 when the domain is large. So I'll spend most of the next hour talking about what we did here. So as Dimitri said yesterday, when I told him there was a spoiler for today, this is the simplest PDE that exhibits spatio-temporal chaotic behavior. But you can prove things. There's a lot of papers, and I'll give you some references later, on existence of solutions for this, bounds and solutions, pretty much any result that you need for the uncontrolled PS equation is there, and then we added the right-hand side of the right form, and we saw, okay, can we control this? So just to bring the point sort of why we are doing this and how we are doing this, so this is a comparison between DNS and Navier-Stokes equations, which I believe and hopefully we'll do tomorrow, which takes, if you're doing it for these values of the parameters, which is when we were trying to break this, it takes a lot of time. This is a simulation of the weighted residuals model, which was up only two equations that for me took a few minutes on my laptop. I'm sure Oscar will do it faster. I'm not going to have him do it because I didn't want it. And here is the Gomes-Mashinsky equation. So I think the first thing to notice is that this is very different than this and that. So, when I was halfway through my PhD and I was like, I can control this, and I went to people and said, I'll do that now, and they're like, I'm not going to do anything based on results from this, because obviously this is different. But this still tells us a lot. First of all, we can prove things here, and this gives us a lot of information. And hopefully, if you learn nothing from today, you'll learn that. Or if you really learn nothing, hopefully I can at least convince you that information from here is very useful and what we're going to do next. So, again, this is not exactly, I think the solution to, this solution would be an unstable solution to this, but I'll discuss that later. The point of this slide is to show that these two solutions actually, so this is space and this is time on both of them, they look very much the same, or similar enough, definitely qualitatively enough. And then what I'm showing you in the bottom plots is on the right, in blue is the DNS and in red is the model of how the interface looks like at the end of the simulation, so they look pretty much the same, so the model is very good. And in this figure, I'm showing you what's happening as a function of time in this point in space. And again, they agree pretty well. So we hope that at least if we can control this model in the middle, we can use those controls to control the rest. That's the hope. And then just to wrap up before the break, just to say, like, yeah, so we're treating this as a hierarchy of models and trying to sort of sell this expression to everyone who listens. So you start by the Navier-Stokes equations, which you can solve with the NS, but you can only do it numerically and it has a large computational cost. And then you have these two levels of long wave-like models that are PDEs for the height and the flux. You can go down to Kuromoto-Smashinsky equation, which is simpler. I just made all the coefficients disappear just to show the singular structure of the equations. And you can actually do, or you can get linear stability only of the initial problem using our Sommerfeld.